Welcome to Shanti-Peace for Mathematics. So in my previous videos, we have talked about the Euler's Theorem. The Euler's Theorem states that f is a homogeneous function of degree m whose first order and second order partial derivatives exist. For that we can write if and only x fx plus y fy is equal to mf. So this was the first result. This is known as the Euler's Theorem that we have discussed, and corollary to that we have discussed that x square fxx plus 2xy fxy plus y square fyy is equal to m into m minus 1f. This is one of the result which we have discussed also. The link for both this result, those who have not gone through the proof for that, it's available in the icon button. You go and see what will be the proof of that. So now the question is, if you have the function given as this u of sine x square plus y square. Now you just note that this u is not an homogeneous function, because you just check that u of tx ty will not be equal to t power any m is there, such that this is happened. So this is not equal to that for any m, so that's why this u is not an homogeneous function. But what we note is this function, that is x square plus y square, is a homogeneous function of degree 2. So here the situation is of this type. U is some function of z, where your z is a function of x and y. So what is the result like Euler's theorem or this corollary we can state? So this video I have done to describe or to solve the equation which involves the partial derivative of such type of functions. So that is also known as a corollary of this Euler's theorem. Let us see what is that corollary is. The corollary states like this: if z is a function of u, which is a homogeneous function of u of f of xy. So here the situation is z is a function of u and u is a function of two variable x and y. U is nothing but the function of f whose second order partial derivatives exist, and also this function capital F, which we have z, is 1 1 on 2 and it's differentiable. Then we need to prove that as like the Euler's theorem, x into ux plus y into uy is equal to m into f of u upon f dash of u, and the second order partial derivatives involves this quantity where this g of u is having this function, that is exactly this function g of u we have got from this expression. So let us try to prove this statement here. So what is given here first of all is this f, small f of xy is a homogeneous function of degree m, as u equal to f of xy is a homogeneous function of degree m. By Euler's theorem we have x fx plus y fy equal to mf. Now what else is given? Also given that z is a function of u, that is the capital F is there, which is 1 1 function. The capital F is 1 1 on 2. Also it is differentiable, that is our hypothesis that we have assumed capital F is 1 1 on 2 and differentiable, that is given. Since this function capital F is 1 1 and on 2, we can write u is equal to f inverse of z. Due to it is 1 1 and on 2, its inverse exists. So I am applying inverse both sides. So we'll have this If you take the partial derivative of this u with respect to x and y, what is the situation? You just see that u is a function of z and z is a function of x and y. Due to this, z is a function of u and u is a function of x and y. So here this is the situation. Ultimately z is a function of x and y. So therefore we can say that del u by del x, by taking the derivative of u with respect to x, will have du by dz into del z by del x. So if I go via this path and this one, this is only a function of one variable, so that's why it is du by dz, and z is a function of two variables, that's why it is del z by del y. If you partially differentiate this u with respect to y, in similar manner you will have du by dz into del z by del y. Now ultimately what we need to do, we need to calculate x ux plus y uy. So we have that quantity here. So I'm starting with that side now, that is x ux plus y uy. As per that we have x into, if I substitute this value and you just note that this du by dz is common out from that expression, so that's why we have du by dz into x del z by del x plus y del z by del y. Now what is the hypothesis also, let us look at over that. Since this z is also a function of, z is also a homogeneous function, because now here the situation is z is a function of u and u is a function of x and y. So that's why this z is also a homogeneous function of degree m. So due to that we can write down this quantity by Euler's theorem, it is mz. So that's why we have du by dz into m into z. Now as we have z equal to capital F of u, if I differentiate this z with respect to u, we'll have, if I differentiate this with respect to u, we have 1 equal to f dash of u into du by dz. So this will imply du by dz will be 1 upon f dash of u. And we substitute that value here, that is du by dz is equal to 1 upon f dash of u. This we can write as mz. What is z? Z is actually f of u upon f dash of u. That completes the proof of the first equality which they have asked to prove, that is x du by dx plus y du by dy is equal to m into f of u upon f dash of u. Now the second equality, that is involving the second order partial derivative. So for that I am taking g of u equal to m into f of u upon f dash of u. So we'll have now situation x into ux plus y into uy. Since this quantity is gu, as per this one, this quantity is gu, so that's why we can write down this is as gu. If I partially differentiate this quantity with respect to x, we'll have x uxx plus ux y u yx is equal to g dash of u into del u by del x. And if I differentiate this equation with respect to y, we'll have x u xy plus y u yy plus uy equal to g dash of u del u by del y. Now if I multiply both this equation by x and this equation by y, you just note that what we will get. We will get is x square uxx, because if I multiply x to here, this will become x square, this will become x ux, that will write in the next line x ux, plus this is nothing but the xy uyx, plus this side now it is xy uxy plus y square uyy, and if you multiply this y to here, this is y uy equal to on this side. Now g dash of u is common out from this, so this is g dash of u into x, if I write down this is in short form as ux plus y into uy. Now we have assumed that this u is a differentiable function, so that's why this uxy is same as uyx. We have assumed the function which having this property, the property which satisfied by the Young's theorem or Square's theorem. The function u is satisfying those property. So that's why we can say that this u of uyx is same as uxy. So we have finally we get x square uxx plus 2xy uyx plus y square uyy equal to g of dash of u into what we have. You just note here, this is x ux plus y uy, x ux plus y uy is g of u, and this quantity is also I am putting as g of u. So here g of u is coming here and here also. So that's why this g dash of u into g of u that you have, and minus g of u, because that quantity was on the other side. So if you common out g of u from it, so it will have g of u dash of u minus 1. So that was the expression that we need to prove. You just check that here we have this double derivative equation involving this, that is x square uxx plus 2xy plus y square uyy is equal to this quantity. So that's complete the proof for this corollary. Let us solve one of the example based on this, which we have discussed earlier, that is this example which we have discussed. Let us try to solve that example. So if the function u is equal to sine of x square plus y square is given to you, and the question is to calculate what is x ux plus y uy, what is this quantity, and also what is uxx plus 2 times 2 times xy into uxy plus y square uyy is equal to what? Which quantity we will have. So here what you can just note that this function is, if I consider as f of xy, which is x square plus y square, you note that this function x square plus y square is a homogeneous, because f of tx ty will gives you t square x square plus t square y square. So that's why it is t square is common out, it is x square plus y square, hence we will have t square f of xy. So therefore we can say that f is homogeneous function of degree 2. Here we have z is equal to sine of x square plus y square. I am applying sine inverse both sides, so this will be nothing but the sine inverse of z is equal to x square plus y square. We have proved that this x square plus y square is a homogeneous function for degree 2. So for that I am just taking this as f of xy. Now if we compare this situation with this corollary, we have here in our example sine inverse of z is equal to f of xy, which is nothing but the x square plus y square we have. So this is your function u. That is, u is equal to f of xy, and this is your f of u. We have f of u equal to sine inverse of u. So according to this situation, I am just writing f of z is equal to sine inverse of z. Now as per that, we have x ux. So here we have x zx plus y zy is equal to m into f of z upon f dash of z. Now m is 2, f of u is sine inverse of z, and f dash of u is the derivative of this quantity, that is 1 upon 1 minus z square. So finally we will have 2 into 1 minus z square into sine inverse of z. Now for the another inequality which involves the second order derivatives, that is x square z xx plus 2xy z xy plus y square z yy will be, which is g of z into g dash of z minus 1. Now what is g dash of z, which is exactly we have here? This is the value of g of z. So if I substitute that value here, that is this here, I need to take what is the derivative of g dash of z. So g of z we have calculated is 2 into sine inverse of z into square root of 1 minus z square. So g dash of z, you will by applying the product rule here, so it will be 2 into sine inverse of z, as it is derivative of square root is 1 upon 2 square root, and the derivative of 1 minus z square is minus 2z by chain rule, plus square root of 1 minus z square, as it is derivative of sine inverse of z is again 1 upon 1 minus z square, and you just note that this 2 is cancel out, this 1 upon z square is also cancel out. So finally you will have 2 into 1 minus z sine inverse of z upon 1 minus z square is the g dash of z. So finally, therefore, x square z xx plus 2xy z xy plus y square z yy g of z into g dash of z minus 1. Now g of z is putting this value here, and g dash of z is also I am substituting this value. This completes the solution for this example. Now we'll solve the next example, but the method for this solution for this example is very different than the other one. U is equal to tan inverse of x cube plus y cube upon x plus y, where x is not equal to minus y due to its domain. Then the question is to find x ux plus y ui. So I am doing this problem not as in the previous manner, but just slightly in the different way. So what we have is u is a tan inverse of this, so we can write down this is tan of u equal to x cube plus y cube upon x plus y. First one should note that this function u is not homogeneous function, but by making this tan u, then this side is a homogeneous function, because we can write down this is as x square 1 plus y by x whole square. So this is another way to check whether the function is homogeneous or not, by doing commoning out what is the maximum power of x. The denominator maximum power of x is x, so that's why it is 1 plus y by x, and so this is x into some function of y by x. So we can say that this tan u is a homogeneous function of degree 1. So by Euler's theorem, we say that x del u by del x of here the function tan u is homogeneous. So that's why it is x del u by del x tan u plus y del u by del y tan u equal to f is tan u, so that is tan u you have. So that's why it is x now so the differentiation of tan u, we know that it is sec square u, so that is sec square u del u by del x plus y. Here is also sec square u del u by del y equal to m tan u, and you just note that this sec square is common out and it divides in the numerator. So if you have this is del u by del x into del u by del x plus y into del u by del y is equal to m into tan u upon sec square u. Hence we have the value of this quantity, which is m into tan u upon sec square u. So that's it for this video. In this video we have discussed that if z is not an homogeneous function but it is a composition of some homogeneous function where this u is a homogeneous function, then you can have the expression similar like Euler's theorem. So that's it for this video. If you have liked this video, please press the like button. If you have any comment, suggestion or question, please drop down in the comment box below. Till then, bye bye. Sayonara. See you in next video.